St. Joseph's College for Women Autonomous, Visakhapatnam, Department of Mathematics welcomes you for the online course on Real Analysis, Modular 1, Real Numbers, Real Sequences, Video 2. My name is Dr. V. Gauri Shankar Rao, MSc MPhil PhD, Assistant Professor, Department of Mathematics, St. Joseph's College for Women Autonomous. Let us see this important theorem on sandwich theorem. So here that sandwich theorem. So sandwich theorem means before how we can solve the problems, I can explain the step by step. You can see that an less than or equal to Sn less than or equal to Bn. Here Sn is the one sequence, An and Bn is. Let us see this. The first step one. The step one is given sequence. You can simplify that. The before one, the given sequence you can simplify. So then you can consider that is called as Sn. So that is a step one. So let us see that step two. Step two means you can assume An. You can assume the An. So this assumed An value you can simplify. That simplification it is matching on Sn value. So the next step 3, you can assume Bn. So this Bn you can apply binomial process. Again that value approaches to Sn. The next step 4. The next one is step 4. By using step 1 and step 2, you can say An less than or equal to Sn less than or equal to Bn. The next step 5. Once you can apply the n tends to infinite in An. You can take the limit n tends to infinite. You can apply in An. You got the some particular value. So means what is that? Limit n tends to infinite An. You got that some particular value. So that is a step 5. The next step 6. The same process you can apply the limit n tends to infinite to the Bn value. You got that some value. Here step 7 is An and Bn values. So the both are the same. You got that both values should be same. So An value is the same and Bn value is the same. Automatically Sn also same. So that is called as a step 8. So this can be treated as like sandwich theorem. So what is the sandwich theorem? An less than or equal to Sn less than or equal to Bn. Sn is the one sequence. So that sequence once you can apply the limit value, got the some value. So at the same time Bn. So this is another sequence. You can put n tends to infinite, you got the some value. So An also the same. You can put n tends to infinite, you got the some value. So the three values should be same. It is called as a sandwich theorem. What is step 1? The given sequence you can simplify. That one is called as a Sn. You can assume. The next you can take An is some assumed sequence. That sequence is simple. After simplification you got that same as usual Sn. So after that you can assume one Bn sequence. That Bn sequence also you can simplify. It is look like as a Sn. After that you can say An less than or equal to Sn less than or equal to Bn. In step 5 you can put n tends to infinite in An, you got the some value. So limit n tends to infinite to Bn, you got the some value. The both values same, automatically the Sn also the same. Why? Because of An less than or equal to Sn less than or equal to Bn. So this is called as sandwich theorem. Let us see the sandwich theorem. So sandwich theorem means what is that? The compulsory you need the three sequences. Let us see this statement. If Sn, Tn, Un are three sequences such that, here what is the statement is? The given one is the three sequences. The three sequences is the Sn, Tn, Un. So first condition, Sn less than or equal to Un less than or equal to Tn. Before I can explain now An, Sn, Bn, but here they can denote as Sn less than or equal to Un less than or equal to Tn in place of that. For n greater than or equal to k, where k is a some positive integer, and the second one is limit Sn equal to limit Tn equal to L. Once you can sub the infinite value, you got that L. The both values should be same. So then prove that limit Un equal to L. So Sn value is the L, the Tn value is the L, automatically Un also L. Why? Because of by the sandwich theorem, Sn less than or equal to Un less than or equal to Tn. So let us see the proof. Given that, what the given one is, Sn, Tn, Un are three sequences such that conditions Sn less than or equal to Un less than or equal to Tn for n greater than or equal to k, where k is some positive integer, and the second one is limit property. Limit n tends to infinite, Sn equal to limit n tends to infinite, Tn equal to L. So limit means the compulsory, you can say it is a convergence, the n value up to infinite. So that's why you can write limit or limit n tends to infinity, the both are same. Now we can prove that limit Un equal to L. So limit Sn is the same value and limit Tn also the same value, automatically Un also same value. Why? Because of condition 1 is the Sn less than or equal to Un less than or equal to Tn. Let us see that. Since already we know that convergence property now, what is the property? Limit n tends to infinite, Sn equal to L for epsilon greater than 0, there exists m1 belongs to n such that modulus Sn minus L less than epsilon for all n greater than or equal to m1. Here you are consider the two sequences, three sequences. That's why you can consider as m1 and m2. But before that, before I going to that S1 Tn, the two sequences. So that's why I can take two existed values. So that existed value m1 and the second value is the m2. Limit n tends to infinite, Tn equal to L for epsilon greater than 0, there exists m2 belongs to n such that Tn modulus Tn minus L less than epsilon for all n greater than or equal to m2. Before going to this, I can take the two convergence property. One is the Sn related, the second one is the Tn related. So let us see this. Let m equal to maximum k comma m1 comma m2. So since Sn less than or equal to Un less than or equal to Tn, so already this is a condition 1, Sn less than or equal to Un less than or equal to Tn. I can apply the minus L, Sn minus L less than or equal to Un minus L less than or equal to Tn minus L. After that I can apply the modulus. So modulus Sn minus L less than or equal to modulus Un minus L less than or equal to modulus Tn minus L. So once it is look like as a convergent property, modulus Sn minus L means what is a less than epsilon. Here each and every sequence it is look like. So that's why I can write the less than epsilon. So modulus Sn minus L less than epsilon, modulus Tn minus L less than epsilon, automatically modulus Un minus L also less than epsilon. So therefore limit Un equal to L. For each epsilon greater than 0, there exists m belongs to z plus such that modulus Un minus L less than epsilon for all n greater than or equal to m. So by the limit property, limit n tends to infinity, Un equal to L. The simply Sn is convergence, Tn also convergence, automatically Un also convergence. So this is a sandwich property. Let us see the problem. Show that limit n tends to infinite, cos n phi by n equal to 0. Limit cos n phi by n equal to 0. We know that minus 1 less than or equal to cos n phi less than or equal to n. So cos n phi value in between, negative value minus 1, at the same time 1. Why? Because of cos n phi means what is that? Minus 1 power of n. Cos n phi equal to minus 1 power of n. You can put n equal to 1, you got the minus 1, n equal to 2, like that, minus 1 power of n. So I can apply the 1 by n. Minus 1 by n less than or equal to cos n phi by n less than or equal to 1 by n. So simple, I can take the fractions like. So minus 1 by n I can treat it as like Sn, and 1 by n treated as like 1 by n. So limit Sn equal to 0, limit Tn equal to 0. By sandwich theorem, cos n phi by n also 0. Minus 1 by n value is the 0. So at the same time limit, once you can sub that n tends to infinity, you got. So at the same time Tn also the same 0. So once minus Sn is the 0, Tn is the 0, automatically Un also 0. So the three values, the three sequence is the zeros, automatically the proved on sandwich theorem. See this one more example on this problem. If Sn equal to 3n minus 1 into n power of 4 minus n by n square plus 2 into n cube plus 1, then prove that limit Sn equal to 3. Here limit means what is that? Limit n tends to infinite. So once you can replace n tends to infinite, the compulsory n value should be denominator. You can remember this point. It is very very important. So let us see this. Limit Sn equal to, both you can take that Sn limit on both sides. You got limit 3n minus 1 n power of 4 minus n square plus 2 into n cube plus 1. Here you can take that n is the common. Once you can take n is the common in numerator, you got 3 minus 1 by n. So after that, in second term, n power of 4 is the common. You got 1 minus 1 by n cube. As it is following the denominator, n square is the common. You have 1 plus 2 by n square. N cube is the common. 1 plus 1 by n cube. So numerator n into n power of 4, base equal, you can add the powers. This is a n power of 5. So denominator n square plus n cube is called as n power of 5. The both are the cancel. So after that, n is replaced by infinite. 1 by infinite value is a 0. 3 minus 0, and this is a 1 minus 0, and denominator 1 plus 0 and 1 plus 0. The both are the cancel. You got the 3 by 1 value is the 3. So limit n tends to infinite Sn value is the 3. Again, you can see the one more problem. Prove that limit n tends to infinite n cube minus 2n plus 1 by n cube plus 2n square minus 1 equal to 1. So again, you can apply the limit n tends to infinity. Before going to this, you can take the n cube is a common. Once you can take n cube is a common, 1 minus 2 by n square plus 1 by n cube. Again, the denominator is the n cube is a common. 1 plus 2 by n square minus 1 by n cube. Both n cube is a cancel. After you can, n is replaced by infinite. 2 by infinite 0, 1 by infinite 0. At the same time, 1 minus 0 plus 0 by 1 plus 0 minus 0 equal to 1. So these problems, once you can, n is replaced by infinite, you can remember that n should be common. Each and every n term is denominator. Without denominator, you can't find that 1 by infinite is the 0. So compulsory you can n value denominator term, must and should, n term should be denominator. So let us see this. This is the sandwich theorem related problem. What is the sandwich theorem means? So Sn equal to L and Tn equal to L, automatically Un also L. You can prove like that. So see the problem. Prove that limit n tends to infinite 1 by root over n square plus 1 plus 1 by root over n square plus 2 plus so on plus 1 by root over n square plus n equal to 1. Here this sequence you can prove it is called as a 1. So let us see this. This total, let our assumption Un equal to this entire 1. So after that, 1 by root over n square plus 1 plus 1 by root over n square plus 1 plus so on 1 by root over n square plus n equal to n by root over n square plus n. So this term should be written as n by root over n square plus n. Here I can take that n is a common. So denominator n is a common. Can I write 1 plus 1 by n root over? So both n is a cancel. 1 by root over 1 plus 1 by n. So let Un equal to, what is the Un equal to? This total term. So this total term, it can be denoted as n by root over n square plus 1. So this n square plus 1, it can be treated as, here you can observe this. This is n square plus 1, n square plus 2, n square plus n. So the second one is n square plus 1 and n square plus 1 and root over n square plus 1. Here also the same denominator n is the common term. The both n is the cancel. You got 1 by root over 1 plus 1 by n square. Sn is the 1 by root over 1 plus 1 by n. The Tn is the 1 by root over 1 plus 1 by n square. So once you can apply the limit n tends to infinity Sn, that value is the 1. You can see that 1 by 0 is the 1 by infinity is the 0. So like Tn also 1. So by the sandwich theorem, Sn equal to 1, the Tn equal to 1. So automatically Un also 1. Already I said, before going to this, you can identify that the before one is how we can identify that by using Un. You can identify that what is the Sn. Okay, at the same time you can identify that Tn. Here I can identify that Sn related and this one, and Tn related is a 1 by root over 1 plus n square, 1 by n square. Here I can sub the n tends to infinite, I got that 1 value. So automatically Sn is the 1 and Tn also 1. The middle value Un sequence also 1. So both values should be same. It is called as sandwich theorem. So let us see this increasing or non-decreasing sequence. So non-decreasing means what is that? It is not a decrease. Once it is not a decrease, automatically it is increasing sequence. Let us see this. A sequence Sn is said to be increasing or non-decreasing if Sn less than or equal to Sn plus 1 for all n. So simply they can say it is an increasing sequence. How we can say the increasing sequence? 1, 2, 3 is there. 1 plus 1 is the 2. 1 plus 2 is the 3. Automatically it is the increasing. So that is the sequence. It can be written as S1 less than or equal to S2 less than or equal to S3, so on. Sn less than or equal to Sn plus 1. It is like highest values. Example, Sn equal to n square. For example, I can put n equal to 1. 1 square value is a 1. N equal to 2. 2 square is a 4. 3 square is a 9. 1, 4, 9 like that. So this series is called as a increasing or non-decreasing sequence. Next, decreasing or non-increasing sequence. Non-increasing means that sequence is not the increase. Once it is not increased, automatically decrease. A sequence Sn is said to be increasing or non-decreasing if Sn less than or equal to Sn plus 1. Here you can observe this the both. Increasing means n plus 1 value is a big one comparing to n value. So decreasing means what is that? N plus 1 value is a small comparing to n. You can remember this both. So automatically that series should be decrease. S1 less than or equal to S2 less than or equal to S3 less than or equal to so on. Sn less than or equal to Sn plus 1. So Sn equal to 1 by 2 power of an. Example, here you can put n equal to 1. 1 by 2 1 by 2. 1 by 2 value is the 0.5. 1 by 2 square 1 by 4 0.25. Automatically it is a decrease. So that's why the sequence is called as non-increasing sequence or decreasing. Next, monotone sequence. Already I said monotone sequence means what is that? Sn is said to be monotonic if it is either increasing or decreasing. The sequence should be either increase or decrease. That type of sequence is called as monotonic sequence. Let us see this very important theorem is this one. Prove that monotone sequence is convergent if and only if it is bounded. Prove that monotonic sequence is convergent if and only if it is bounded. Monotonic means what is that? Either increasing sequence or decreasing sequence. The compulsory is a sequence. Once the sequence is given, they said what is that? Convergent. Once it is a convergent, it is a bounded. Why? Because of convergent means what is that? Modulus Sn minus L less than epsilon. Modulus is there, automatically negative value is there, at the same time positive value. So minus L less than Sn less than L. So minus L is the lower boundary, L is the upper boundary. In between Sn is there. So that's why automatically it is a bounded. So let us see the proof. Let Sn be a monotonic sequence. Suppose that sequence Sn converges to L. Now we prove that Sn is the bounded. So first Sn is the monotonic sequence. The second one, what you can assume? Sn converges to L. Once Sn is a converges to L, what you can prove? Sn is the bounded. Bounded means how we can prove? You have the minus value at the same time plus value. It is not a minus, lower value at the same time upper value. In between Sn is there, it is a bounded. So sequence Sn converges to L, limit n tends to infinite Sn equal to L. This is a convergence property. Limit n tends to infinite Sn equal to L. What is the condition? For each epsilon greater than 0, there exists m belongs to n such that modulus Sn minus L less than epsilon for all n greater than or equal to m. So compulsory it is a convergence that m value should be n greater than or equal to m. Why? Because of n is the last term in sequence, but m is the either middle or in between term. So once m is the existed on in n. So let us see this. Modulus Sn minus L less than epsilon, how we can write? Minus epsilon less than Sn minus L less than epsilon. Why? Because of modulus is there. The limit in between negative to positive. After that I can apply the L on both sides. L minus epsilon. Here the negative L and positive L is a cancel. You got L plus epsilon. So the L minus epsilon is the lower value. L plus epsilon is the upper value. So Sn is existed on lower at the same time upper. So therefore Sn is the bounded. Conversely, suppose that Sn is bounded. What you can consider actually, you are taken by convergence. Finally what you can prove? It is a bounded. So conversely, what you can conversely, you can take the bounded. So they can say it is the convergent. So let us see this here, that very important one. So convergence is the bounded. Bounded is a convergent? No. But what you can prove here, bounded sequence, your consideration bounded, but you can say it is a convergence. Let us see this, how it is possible. If Sn is increasing sequence, monotone means what is that? Either increasing or decreasing. Let us see this increasing. So once it is increasing sequence, it is a bounded. Bounded, you can say it is a convergence, but it is impossible. But you can see that how it is. Sn as supremum, say k. So what you can consider is a bounded. Sn has the supremum, say. Here what is the supremum? The supremum means least upper bound value. Least in upper bound. You can assume that upper bound, but in that sequence you can take the least. So Sn as the supremum, say that value is k. K minus epsilon is not an upper bound of Sn. What they said, supremum k is the least upper bound, but k minus epsilon, you are removing the some epsilon value in that k. In that time it is a upper bound, so it is not a upper bound of Sn. There exists m belongs to n such that Sm greater than k minus epsilon for epsilon greater than 0. So k is a supremum value. One remove that minus epsilon, it is not an upper bound. Therefore Sn is increasing. Once Sn is increasing, can I write Sn less than or equal to Sm? So for all n greater than or equal to m, so Sm is existed. So since Sn greater than or equal to Sm, so in that time it can be written as Sm greater than k minus epsilon. So this one it can be written as Sn greater than k minus epsilon for all n greater than or equal to m. So since supremum Sn is k, implies Sn less than k plus epsilon. Since Sn less than k minus epsilon, comma Sn less than k plus epsilon implies k minus epsilon less than Sn less than k plus epsilon for all n greater than or equal to m. So implies minus epsilon less than Sn minus k less than epsilon. Here you can remove the k value. So automatically what is that? Modulus Sn minus k less than epsilon. So for all n greater than or equal to m, so limit Sn equal to k. So therefore Sn is convergent to k. But here you can observe that Sn is the bounded sequence. Sn is the bounded sequence. Once Sn is the bounded, automatically got that lower value and upper value. But once you can take the lower and upper both values, it is not a convergent. Why? Because of there two values is existed, but here the logic is there. First you can take supremum. Supremum means what is that? Lower upper bound value. So lower upper bound value. You can consider lower upper bound value. In that lower upper bound value, you can remove that minus epsilon. Once you can remove that minus epsilon, automatically that value should be single existed value. Once it is a single existed value, then it is a convergent. So that is the main. Is it clear that point? So there are taken Sn as a supremum. So once Sn is a supremum, that value is a k, you can remove that minus epsilon. Once you can remove that minus epsilon, so automatically that value is converted as a single value. Once it is a single value, it is a convergent related. So that's why the final you can prove modulus Sn minus k less than epsilon for all n greater than or equal to m. So therefore Sn is convergent to k. Let us see the case 2. If Sn is decreasing sequence, what is a monotonic means? Either increasing or decreasing. Already increasing or you are proved by convergent. Let us see the decreasing sequence. So Sn is a bounded. Sn has infimum. What is the infimum means? So infimum means that supremum means what is the least upper bound. Infimum means what is it? Greatest lower bound. Greatest lower bound. Once you can observe that supremum infimum at a time, you have that only single value. So Sn has infimum, say L. So here you can take that L plus epsilon is not a lower bound. So L means what is it? Greatest lower bound. Greatest lower bound. But once you can add the epsilon, automatically is not a lower. Why? Because of the value should be increased. L plus epsilon is not a lower bound of Sn. There exists m belongs to n such that Sm less than L plus epsilon. For epsilon greater than 0, Sn is decreasing, Sn less than or equal to Sm. So let us see this. This is infimum related. That's why I can consider as Sn less than or equal to Sm. Comparing to n, Sm value should be more. Sn less than or equal to Sm. So what is the value? I can take that epsilon. Sm less than L plus epsilon, it can be treated as Sn less than L plus epsilon. So inform of Sn is L, Sn greater than L minus epsilon. Sn greater than L minus epsilon, it can be treated as Sn less than L plus epsilon. So implies 1 minus epsilon less than Sn less than L plus epsilon for all n greater than or equal to m. So you can remove that L, you can add the L on both sides, you got minus epsilon less than Sn minus L less than epsilon. So once you can write like this, modulus Sn minus less than epsilon for all n greater than or equal to m. So therefore limit Sn equal to L. So therefore sequence Sn is convergent to L. Before increasing sequence, decreasing sequence, you can observe that. So in supremum value you can remove that minus epsilon, but here infimum value you can add the plus epsilon. Once you can add the plus epsilon, automatically that value, it is a bounded value, it is converted as a single value. Once it is converted as a single value, automatically it is a convergence existed. Once you can take the bounded as it is not a convergence. Why? Because of the two values is existed. But once you can take that individual infimum value, so that infimum value you can add the some plus epsilon, automatically it is some particular value. So in that particular value, automatically, so it is a convergence. So that's why the bounded sequence is a convergence. Actually bounded sequence is not a convergence, but in this case the convergence. Why? Because of you are adding plus epsilon, you are removing that minus epsilon, automatically you are equating one value. For example, the 2 is there, so but L value is a 1.5. So 1.5 to 2, 1.5 is the lower value, 2 is the upper value. So 1.5 existed, 2 also existed, but it is not a convergence. But you can equating the 2. How we can equating the 2? Just you can add the epsilon means 0.5. 1.5, 0.5 is the 2. It is a new value. That new value is a 2. 2 automatically it is a existed. So that basis on, you can say it is a bounded sequence also convergence. Let us see that divergent sequence. What is a divergence means? The sequence is not a convergence, automatically it is a divergent. A sequence which is not convergent is called divergent sequence. Divergent sequence are classified as two types. One is a divergence to infinite. Second one is divergent to minus infinite. The third one is oscillating. Once you can sub n tends to infinite, you got that infinite value. So it is called a divergent. Otherwise minus infinite. This one also divergent. Otherwise oscillating. And this one also divergence. Oscillating means what is it? Negative to positive and positive to negative. So it is called as a divergence. Divergent to infinite. Let us see the divergent to infinite. A sequence Sn is said to be divergent to infinite if for each epsilon greater than 0, there exists m belongs to z plus such that Sn greater than g for all n greater than or equal to m. So divergent to infinite means Sn equal to n square. So Sn is a divergent, the compulsory they can exist Sn greater than g. Divergent to minus infinite. A sequence Sn is said to be divergent to minus infinite if for each epsilon greater than 0, there exists m belongs to z plus such that Sn less than minus g for all n greater than or equal to m. Example, Sn equal to minus n square. The simple here you can put n equal to infinite. What is the value? Infinite square is the infinite. Here you can apply that n equal to infinite minus infinite square. Minus infinite square also divergent to minus infinite. So oscillating sequence. A sequence Sn is said to be oscillating if the Sn is bounded and not convergent. Sn equal to minus 1 power of n. Why? Because of it is a minus 1 treated as like as a infinite. But once you can take minus 1 power of n, you got minus 1 and 1. The two are existed. So that's why oscillating sequence also divergent. But you can remember that convergence means you got the finite value. So that finite value should be unique. But here oscillating sequence is the minus 1 comma 1. So that's why it is a divergent. So here the minus infinite square. So that's why this one also divergent. Here that you can put n tends to infinite, you have that infinite square, and this one also divergent. The simply remember that you got that finite value after n tends to infinite, this is a convergent. So it is not a finite, it is an infinite value or oscillating related values, it is not a, it is a divergent. Is it clear? So every bounded sequence is either convergent or oscillating finitely. Every bounded sequence either convergent or oscillating finitely. So that one is very important note point. Already it is proved theorem. Let us see the some problems. The first problem is prove that the sequence Sn equal to 3n plus 4 by 2n plus 1 is decreasing and bounded below. So that sequence you can say it is a decreasing. At the same time you can say it is the bounded below. So let us assume the compulsory here the two terms you need. Why? Because of you are comparing. So how you can say it is a decreasing, increasing? The compulsory need the two values. Here also I can consider two sequences. So Sn equal to the given one, I need that Sn plus 1. Sn plus 1 means the next term. How we can say it is the next term? N is replaced by n plus 1 on nth term. So I got n plus 1 term is the 3n plus 7 by 2n plus 3. So the condition is Sn plus 1 minus Sn less than 0. Once you can remove that, n plus 1 is a big value, n value is a small value. One you can remove that, highest value minus lowest value equal to positive now, but here negative. So that's why the series is called as a decreasing. So once you can simplify this, you got, it is like LCM method, you got minus 5 by 2n plus 3 into 2n plus 1. Once you can replace n equal to any value, got the negative value. Once it is a negative value means what is it? Less than 0. Once you got that less than 0, the compulsory the sequence Sn is decreasing. Remember this point, Sn plus 1 minus Sn less than 0. N plus 1 is the highest value, n is the lowest value. Highest value minus lowest value is the some particular value, but here it is a negative value. Once negative value comes, it is a decreasing sequence. Next you can say it is a bounded below. So Sn is the 3n plus 4 by 2n plus 1. Here how we can take that? So 3 by 2 into 2n plus 1 plus 5 by 2 by 2n plus 1. Here I can write like this. 3n plus 4 it can simplify like this. So after that 3 by 2 two terms you can divide. 3 by 2 2n plus 1 2n plus 1 I cancel. 3 by 2 plus 5 by 2 by 2n plus 1. Here I can substitute that n is already denominator. You can put n tends infinite. So it is greater than 3 by 2. So this value compulsory. Once you can observe this value greater than 3 by 2. So that's why automatically it is the bounded below. So the given problem is decreasing. Already it is a bounded below. So at the same time prove that the sequence Sn equal to 3n minus 1 by n plus 2 is increasing and bounded above. So you can say it is increasing. At the same time you can see the bounded above. Again you can need the two terms. One is Sn related, the second one is a Sn plus 1 related. Sn equal to what is that? 3n minus 1 by n plus 2. Sn plus 1 equal to n is replaced by n plus 1. After simplification you got 3n plus 2 by n plus 3. Now we can solve Sn plus 1 minus Sn greater than 0. Less than 0 means what is a decreasing sequence. Greater than 0 means what is that? Increasing sequence. Therefore sequence Sn is increasing. Now we can say it is the bounded above. How we can say it is a bounded above? What is the Sn equal to? 3n minus 1 by n plus 2. So here you can take the 3 is a common, n plus 2 minus 7. Once you can simplify in numerator, it is equal to 3n minus 1. So after that you can divide as a two terms. N plus 2 is a common, cancel. 3 minus 7 by n plus 2. So this value should be less than 3. Why? Because of you can remove the value on this 7 by n plus 2. So automatically it is a bounded above. So therefore Sn is convergent. Next problem you can see that prove that Sn equal to 2 minus 1 by 2 power of n minus 1 is convergent. Sn is the 2 minus 1 by 2 power of n minus 1. Sn plus 1 means n is replaced by n plus 1. You got 2 minus 1 by 2 power of n. The properties Sn plus 1 minus Sn greater than 0. Why? Because of you need some particular value. So once you got the particular value after n tends to infinite, the compulsory it is treated as like convergent. So after simplification of this you got 1 by 2 power of n greater than 0. So therefore sequence Sn is increasing. Once sequence is Sn is increasing is bounded above. So once it is a bounded above, so you got the particular value. So it is a particular value. So that's why the sequence Sn is called as convergent. See this one more example. Problem, if Sn equal to 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4, so on 1 by n into n plus 1, then prove that Sn is convergent. So this total sequence you can treat it as Sn. After n is replaced by n plus 1, you got 1 by n into n plus 1 plus 1 by n plus 1 into n plus 2. What is the condition? Sn plus 1 minus Sn greater than 0. You can prove like that. So Sn plus 1 value is this is the total sequence. Sn is this sequence. You can minus. After that you got 1 by n plus 1 into n plus 2 greater than 0. So therefore Sn is increasing sequence. So Sn equal to 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus so on 1 by n into n plus 1. You can remove that 1 minus. So automatically less than 1 is upper bound. Once you can remove that 1 minus, automatically is lower. So therefore Sn is the bounded above. So therefore Sn is the convergent. Let us see this one more example. Prove that Sn is sequence Sn where Sn equal to 1 by n plus 1 plus 1 by n plus 2 plus 1 by n plus 3 plus so on plus 1 by n plus n is convergent. This sequence you can say it is a convergent. So once you can say convergent, how we can put Sn plus 1 minus Sn greater than 0. Once you can take the condition n plus 1 term, highest term minus lowest term, it is compulsory positive. Once it is a positive, the given sequence should be as a increasing, the same formula. Sn means it is a given sequence. Sn plus 1 means how we can say n is replaced by n plus 1. You got like this. After that, you remove the given sequence minus n plus 1 sequence. Finally, you got 1 by 2n plus 1 into 2n plus 2 greater than 0. So once the condition Sn plus 1 minus Sn greater than 0, automatically the sequence Sn is the increasing. So in that time you can say bounded above. How we can say the bounded above? Let us see this. So this is a given sequence. So this given sequence less than 1 by n plus 1 by n, so on like n by n. N by n value you can cancel the n by n, you got that 1. So Sn less than 1. So for all n. So therefore Sn is bounded above. So at the same time Sn is convergent. The given sequence is a bounded above. At the same time the given sequence is the convergent. So let us see this. The first you can say the increasing. Once it is an increasing sequence, it is a convergence. Once the particular value, the convergence is existed, you can say it is a bounded above. That value should be bounded above. Let us see this one more problem. Prove that the sequence defined by Sn equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus so on plus 1 by n factorial is convergent. So this sequence you can say it is a convergent. So convergent means the same property. What is the property? Sn plus 1 minus Sn greater than 0. Sn plus 1 minus Sn greater than 0, it is an increasing sequence. Let us see this. What is the given sequence? Up to 1 by n factorial. Next n is replaced by n plus 1. You got 1 by n factorial. Next term is a 1 by n plus 1 factorial. Here don't put n equal to n plus 1. Why? Because of the series is ending with n factorial. What is the next term? N plus 1 factorial. Before one is not a n related. It is a particular some values, n by something whatever it is. So that's you can put n equal to some value. But nth term after you can put n plus 1 factorial. Then you can substitute that Sn plus 1 minus Sn. The finally up to n factorial is a cancel. You got 1 by n plus 1 factorial. 1 by n plus 1 factorial is a positive value now. So greater than 0. So therefore sequence Sn is increasing. So what is the given one? Sn is up to 1 by n factorial. So therefore it can be written as 1 plus 1 by 1, 1 by 2 plus 1 by 2 square plus so on plus 1 by 2 power of n minus 1. So here you can write as 1 plus. So this total sequence it can be written as 1 plus of 1 into 1 minus 1 by 2 power of n by 1 minus 1 by 2. So once you can simplify this, you got 1 plus 2 into 1 minus 1 by 2 power of n. So here 1 plus 2 minus 1 by 2 power of n minus 1, 1 plus 2 value is the 3, 3 minus 1 by 2 power of n minus 1 less than 3. You can remember this, 3 is the upper bound. 3 minus 1 by 2 power of n minus 1 is the lowest upper bound like. So therefore Sn is a bounded above, automatically Sn is the convergent. So 3 is the bounded above. So this is a bounded value. 3 minus 1 by 2 power of n minus 1. So automatically one particular value is existed. Then sequence Sn is called as convergent. Let us see this one more problem. If Sn equal to 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 cube plus so on 1 by 3 power of n, then prove that Sn is convergent. The same. Once any problem is given, the sequence is a different, but you can remember that the formula is the Sn plus 1 minus Sn greater than 0. You can say increasing sequence or decreasing sequence. Once you can say that bounded above related, increasing. Otherwise, either you can remember that supremum or infimum related. So let us see this. Sn means what is that? 1 plus 1 by 3 plus 1 by 3 square plus 1 by 3 cube, so on 1 by 3 power of n. N is replaced by n plus 1, you got like this, up to 1 by 3 power of n plus 1. The both sequences you can do the minus, you got 1 by 3 power of n plus 1. Why? Because of up to 1 by 3 power of n is a cancel. The final you got 1 by 3 power of n plus 1. This is a positive value. Once it is a positive value, you got that increasing sequence. The given sequence is the increasing or decreasing, but once the sequence is there, automatically it is a convergence. Let us see this. So what the sequence is? 1 by 3 power of n. Here this sequence it can be written as 1 into 1 minus 1 by 3 power of n and 1 minus 1 by 3. So both it can be written as 1 minus 1 by 3 power of n by, it is simplification 2 by 3. So 2 by 3 it is a reverse, and 3 by 2, 1 minus 1 by 3 power of n. So it is multiplication of 3 by 21 is the 3 by 2 minus 1 by 2 into 3 power of n minus 1. So this particular value less than 3 by 2. This particular value less than 3 by 2. So therefore Sn is bounded above. So 3 by 2 is the bounded value. So bounded above value. So automatically it is a bounded value. 3 by 2 minus 1 by 2 power 1 by 2 into 3 power of n minus 1 less than 3 by 2. Compared to this one is a big value. So therefore Sn is bounded above. So once it is a bounded above, therefore Sn is convergent. Therefore the given sequence is a convergent. Thank you all for watching this video.